Okay, I guess I like to talk about something about infinity. So in another video, I talk about that if we are considering loopback integral for a function like gx, where x is 1 when x is a rational number or 0 when otherwise, then we need to consider the measure of, let's say the measure would be like measure of like all the rational number within the interval 0 and 1, and I claim that this is equal to 0 because like for all the irrational number, let's say from 0 to 1, this is all the irrational numbers, the measure is 1 because we simply, by the way, this is the set of irrational number between 0 and 1, and this is basically set of rational number between 0 and 1. So I claim that like there will be way more irrational numbers than rational numbers. So therefore, like the measure for this guy will be for rational number will be 0, and for irrational number it will be 1. And so I guess I didn't give an explanation for that. But basically, what's going on is like in general, rational number and irrational numbers are in two different I forgot what's the formal word for that, but I can say like order of like infinity. So precisely, rational number is countably infinite. So where irrational number is uncountably infinite. So, and that's why we have so much more irrational number compared to rational number. And of course, I guess I assume you guys already know what's rational number and irrational numbers. So basically, rational numbers all the numbers can be represented as some kind of as a fraction. So for example, like I can say like 9 over 11 is rational because I can represent it as a fraction. And for example, I say pi there's approximately 3.14156. I forgot now, like 141. I just 3.1416. I say, and there's many more digits afterward, and it's irrational because it cannot be represented by any finite number of like of fraction, in the sense that it's equal to some numerator over some denominator of any finite size of numerators and finite size of numerator and denominator. So and yeah, this is irrational and this is rational. So we say something accountably infinite. It's basically we can count it. We can put an index for that, and then so and eventually we can count all of them basically. So therefore, like we say, it's countably infinite. So why rational number is countably infinite? Because we can think of all rational number, because basically all the fractional numbers can be represented by, let's say, this is the numerator, and this is the denominator, let's say. I don't know how to spell it anyway. So I have 1, 2, 3, 4, 5, 6, let's say 1, 2, 3, 4, 5, 6, and I can write a table like this, like 2 over 1, 3 over 1, 4 over 1, 5 over 1, 6 over 1, and this is what? Sorry, 1 over 2, 2 over 2, 3 over 2, and so on and so forth. This is will be 1 over 3, 2 over 3, 3 over 3, 4 over, 1 over 4, 2 over 4, and so on and so forth. So you see the idea here. Of course, there will be like some double count here, but we don't care. It's okay to double count. But the point is like for all the rational numbers can be tabulated like this huge table here. It will go all the way to infinity. But now if we try to count it like zigzag way, like say like this index 1 and this is index 2, this index 3 and so on, then basically we can really count everyone. So all of them will be assigned with an index. So all the rational numbers will be assigned by a index whatever. For example, like I have this is 3 will be equal to have an index 1, 2, 3, 4, 5, 6, have an index 6, let's say. So the key point here is like all of them will be assigned with an index, therefore will be countable. So therefore all the rational number is countable. So it's infinite, but it's countably infinite. Now how about for irrational number? Irrational number will be every numbers that cannot be represented as a kind of a fraction, right? So let's just consider all the irrational numbers because it cannot be represented as a fraction. So I will have basically infinite number of digits afterwards, after the decimal place. So let's consider just all the irrational numbers from 0 to 1, and then like I can represent, let's say 0.1, 2, 3, 4, 5, let's say, and something blah blah blah. I can tabulate that like 1, 2, 3, 4, 5 here, or something like that. This will be a irrational number, 0.125 something tabulated in. Let's say this is the first irrational number I try to tabulate it. Now let's try to again, like as in the rational number case, try to see if we can build a table that will count all the irrational numbers. So let's say eventually I just pick an arbitrary orders, and let's say I have the second one is 0.2, 5, 6, 7 something. So I have the second number is like that. I have the third number, let's maybe like 0.4, 1, 2, 6, 7, 6. Then I have 4, 1, 2, 7, 6 here, and so on and so forth. Maybe I have 5, 1, 3, 1, 5 is 6, and 1, 2, whatever. So let's assume that the premise here is that we first assume that like all the irrational numbers are countable. So therefore we can build a table for that. So now we're trying to contradict ourselves that building such a table is impossible. Let's say we can really build such a table and that include all the irrational numbers. So if it's possible to build such a table that include all the irrational numbers, then the irrational numbers will also be like countably infinite. But now let's say I already have the table. Now let's consider a number that simply pick all the diagonal digit but shifted by 1. So let's say I will pick shifted by 1, I will have 0, let's say 2, and this shift by 1 6, and then 2 will be 3, 2. Let's say if I have a 9 here, I shift by 1, I will shift to 0, let's say, and so on and so forth. Now this number is inside 0 and 1, but apparently it won't be in the table, right? Because it always have at least one digit is different from any numbers on this table. So therefore, like no matter how you build such a table that going to count all the numbers, I can always construct one numbers unwanted irrational numbers does not belong to this table. Therefore, that means that building such a table is impossible, and simply irrational number is not countably infinite, or is uncountably infinite. So because it's uncountably infinite, it's actually it's an order of magnitude bigger as an infinity than the countably infinite one. So therefore, we simply have many more of irrational numbers compared with rational numbers, and that's give the reason why the measure of all the irrational numbers between 0 and 1 will basically contribute all the measures basically will be just equal to 1, and the measure of all the rational number there will be just will only contribute 0, basically contribute nothing. And that's what I like to talk about today. Thank you for watching.